Hi, on this video I'm going to try to show you guys an example of using the how to solve a physics problem steps to solve a problem. Now this is to be used not to solve a problem for which you do not know the solution. That's what you use design thinking or the scientific method for. This is for when you already know how to apply a formula to a certain problem and they give it to you. If you don't know the formula, you can't do this. Now, here's a simple problem in physics. A small airplane starts from rest and must reach a speed of 40 meters per second to take off successfully. Assuming a plane only has 800-meter runway, how fast must it accelerate? So the first thing you want to do is literally read the problem like we just did. Then, as you read to, you can convert the information that's given to you into symbols. Let's try to do that. So, a small airplane starts from rest. So we know that the plane's original velocity is only going to be 0 meters per second. We also know that it must reach a speed of 40 meters per second. That means the final speed of the plane must be 40 meters per second. Assuming the plane only has an 800-meter runway, so we know that it has a distance that it can run of 800 meters, right? How fast must it accelerate? So you see, now we know that it wants the acceleration. I usually even put what it needs to know as the unknown, and I list that as what is mentioned. So anything that is mentioned, any physical quantity that's mentioned, even if it's not given, I will list it. I would just put it as an unknown. All right? So our next step is to conceptualize this problem. That means try to figure out what area of physics this is about and visualize the problem and try to see what I have to do to solve this. Now, this seems to be involving acceleration, displacement, velocity, so I'm guessing this is a motion problem, and more specifically, since it doesn't talk about forces or doesn't talk about collision or rotation, this is kinematics, right? So, and it has acceleration in it, so it's a motion with constant acceleration most likely. So my mind immediately goes to that area of physics, and I visualize what's happening here, right? The plane is trying to take off on a runway, and it has a limited space to do so. So I need to know how quickly it needs to pick up speed in order to do this, right? So I know this is a kinematics problem. Now, it helps because in kinematics, basically you're only going to have these things. Displacement, you're going to have acceleration, velocity, and also sometimes you have time. And the problem makes no mention of time. And that's going to be important in a second as well. Now, the next thing I want to do is diagram with symbols what I saw in this problem. It helps a lot to do that. It also helps further that visualization that I talked about. So I'm going to do that over here. So you have a plane, right? I'm going to represent the plane by this dot over here. And it needs to get to a certain spot where it needs to take off. But that distance that it has to do this is only 800 meters. So that's my displacement. There is no mention of time in the problem. And I know that the original velocity with which it launches is 0 meters per second. But that when it gets over here, by the time it's taking off, it must have, right before it starts taking off, it must have a velocity of at least 40 meters per second. That means it needs to get from 0 to 40 meters per second in 800 meters. And I don't know how long that takes. That's not part of the problem. What I need to know is the acceleration that it must have to do this. So there you go. I converted the symbols into the diagram. Now, when you get good at solving physics problems, one thing that you can do is you can skip the step that you list them and go straight to this diagramming step. But I always like to make sure that I list the unknowns, right? Visualize and identify the area of physics that that's about. The next thing that I need to know is identify the necessary formula to do this. All I have to do is think about the provided quantities, the desired quantities, or any other things I don't know to do this. So here's the things that I have. This is what I want, and I'll put that in a box to help me focus. And I also know that I don't have time. So I can go to a formula sheet if I have one, or if I have one in my head, and I can just use that. What I don't have here is time. So when I'm doing a kinematics problem, that helps a lot. So I don't have time. The no time formula in kinematics is this one, right? So in kinematics, this is a very useful way to find out what formulas you need. All you have to look at is where there is what's not given to you at all in the problem, not mentioned at all, and that usually helps to identify the equation you need to use. In other areas of physics, usually it's by focusing on the knowns and unknowns that you can do that. But you can do that here as well. Notice I have this. I was given a 0 meters per second. I have this because I was given 40. I have the acceleration is, well, kinda, it's what I want to know, and I do have the displacement. So if I have my knowns, and that's my unknown, I can figure out that this is the right formula to use. So there you go. I completed my next step. Now my next step says, cancel out values in the formula that have no magnitude or a 0 value cancellation. So if I look at the formula and my givens, I can notice that velocity initial is 0. So I can go ahead and cancel this value because it doesn't going to factor, right? Now, my next step is to solve the problem algebraically to find the desired quantity. So I'm going to solve the formula algebraically. So what I want is to get acceleration. So I got to get acceleration by itself. So what I'm going to do here, first of all, is divide both sides by 2 delta x, right? So if I do that, my next step is going to be velocity squared over 2 delta x. I don't need that anymore because I canceled it out, equals a. And there you go. I have algebraically solved for my unknown, right? Very good. I did it both steps at once, and I hope you're comfortable with that. So just a little bit of algebra there. Now, my next step, according to this, is to plug in numbers and perform a dimensional analysis with the units. So at this point, I'm going to plug in the numbers, but I'm going to make sure to include the units when I'm doing this. All right, so let's go back to our numbers. Our initial velocity is 0. That's canceled out. Our final velocity is 40. That's what we got to put over here. So 40. And remember, I'm going to include the units. 40 meters per second divided by 2 times. Now I want the displacement, and our displacement was 800 meters. So there it is, 800 meters equals acceleration. All right, so we're almost there. Now, the next thing that we need to do is compute the final answer, and remembering to do that dimensional analysis as we go along. What they mean there is actually do math with units. I might do another video about that at some point, but what we have here, if you pay attention, is meters on the top and then meters on the bottom, right? So that means that this meter up here will cancel out, oops, made a mistake. That happens sometimes. Notice that a formula here has the square. I'm glad I made a mistake in the video because now you can realize, see, I stopped there and I realized there is something wrong. I'm actually going to go on with the problem as if I did not notice the mistake, because then you can see why dimensional analysis is so important. So I canceled out meters. I was about to cancel out meters with meters, right? So if I do that, if I cancel out meters with meters, all I'm left with is 1 over seconds on the top. In other words, my final unit for acceleration would have been 1 over second. And that's not right. You're not supposed to get 1 over second as your final answer. That doesn't make sense at all. And so that means acceleration is supposed to be in meters per second squared. So I know that I did something wrong in the problem. That's what dimensional analysis is all about. It's about using numbers and units in your problems so that you can track your final answer. And it was one of the reasons why dimensional analysis is so useful. All right, so this is wrong. So let's actually fix what's the problem here. The problem was I left a square out. So right, the velocity needs to be squared. So this thing right here, when I plugged in, I forgot to put the square. So you gotta be careful about that, but look how dimensional analysis can help, right? Now if you square that, what you really have here is meters squared and seconds squared, right? So then when I'm doing the math with units, that's going to matter. And I'm gonna go ahead and do that. I'm gonna solve over here. So what I have on the top is 1600 meters squared seconds squared, right? I squared the units as well. That's what dimension analysis means, to do the math with the units. And on the bottom, I have 2 times 800 meters, so that can just become 1600 meters. Things that don't have units don't alter the units when you multiply them together, so you're just going to, it's just a constant, right? So you just get twice as much space. Now we can go ahead and cancel out the units. This meters cancel out with one of the meters from the top, right? And then we're good, because we're going to be left with meters per second squared is the only thing that's left. Now, meantime, we have 1600 on the top, and we have 1600 on the bottom, so that just becomes 1 over 1, which means our final answer for acceleration is 1 meters per second squared. And there you go. So I computed the final answer. Now I can give the final answer with units, which I did already. Now I have to consider significant figures and rounding, right? And also consider orders of magnitude and check my answers. So what this means is that, let's look through the problem. When I started, I was given a number with one significant figure here, and I can talk about significant figures in class or in other videos at another point. And I have another number here with only one sig figure. So it looks like the entire problem is given in one significant figure. So when I get to my final answer, if I had more than one significant figure, I would have to reduce it to a single significant figure. But that's what I already did. So I'm good with my significant figures, right? I'm good with my unit. Right? I don't have to round anything, since I didn't have to reduce significant figures, and it was a whole number in the first place. As far as orders of magnitude, now I stop to think about the problem. Does it make sense for an airplane, small airplane, to only have to accelerate at 1 meter per second square? Well, it's a pretty small number, but if you think about it, this plane doesn't really need too much speed to take off, right? It only needs about 40 meters per second. So and it has a lot of space for a small plane, 800 meters to take off. So a lot of small planes will take off in less distance than that. So this airplane would be able to do it on this larger runway with such a small small acceleration. Right? So, but if you got a number here that was like, say, 100,000 meters per second, well, that's insane. Right? That's a more acceleration than the space shuttle probably has, so that wouldn't make sense. So, like, considering orders of magnitude is looking at the size of your final answer and what base 10 it is. This is just like even less than 10 to the first power, right? And that kind of makes sense for the acceleration of a plane to be in the first order of magnitude, or even that's actually the 0th order of magnitude, because it's just 1. That makes sense. If it was in the 5th order of magnitude, that would not make sense, right? So I always take that step back at the end of my problem to think about that. And then I also check my answer. I can actually plug in, if I want to, on the original formula, right, all the numbers, and see if it checks out. And if you have time, you can do that. I'm not going to do that in this video, but that's just basic math that you can probably learn in the math class, hopefully. The last thing that we can do is explore limits and think about what we have learned from this problem and how can it be applied to real life. And I always like to take a moment to do that when I'm done solving a physics problem. So, well, one thing that I can think of is that this means that small planes don't need a lot of space to take off, right? Those small planes can actually do it in small airports. But if this was a larger plane, I would probably have a problem with that. So that's what explore limits means. Thinking about what other kind of problem would this be involved? What other questions could I ask? And how is this important for real life? So that's solving a physics problem, an example of how to do it. I hope this is helpful.